If you were to Google how to find a rocket center of pressure, you will likely come across two sites. One is a document that gives you this equation. The other is a NASA-hosted site whose funding ended in 2004 and which has since been made inaccessible for my Wi-Fi network, but not my mobile carrier, so haha, government, I can still access your educational page on rocket physics. But I digress. On the surface, it kinda looks like the original model for the Sonic movie. But what if I told you it was just a weighted average? You heard that right. This seemingly terrible equation is, in its most simple form, a weighted average formula of the centers of pressure for each component. So now terrible Sonic is looking a little more like better Sonic. We have the normal force on the nose cone, its distance from the reference line, and the normal force on the body and fins times the distance to the top of the fins. And that's it. We can eliminate two of these terms as we won't be using a conical shoulder or boat tail. So then you can see that solving this is actually quite simple. Let me preface this by saying that the normal force, although being defined with this equation, can actually be defined only with this variable. This is proven valid through this mostly readable derivation, which I'm not going to go through in detail and explain, but basically every term from that first equation except for the c cancels out. Therefore, the center of pressure can be used in place of the normal force like a synth from Fallout 4. We start by getting all the dimensions of our rocket because, well, we're going to need them. Then we follow up by drawing a diagram as it's much harder to see where everything comes from without it. We must then define the reference line. This line is imaginary, much like a critically acclaimed Jurassic Park sequel, and is placed either at the top or bottom of the rocket, serving as our origin or where distance equals 0. I'll put mine at the top, right above the nose cone. Since we're already at the top and it's the easiest, let's start with the nose cone too. Using the document I just showed, depending on your shape, you'll use one of three formulas to find the distance from the reference line, which is called x bar, not to be confused with a triple x bar. We had an ogive-shaped nose cone, so that's the equation I'll be using. We'll calculate that and set that value aside for now. The document also states that the normal force on any shaped nose cone is generally identical and just defines it as 2. No units, just 2. Next we have the fins and body. These come as a package deal, kind of like North Korea and Russia. Wait, that's a different kind of rocket science. Anyways, we'll start by finding the center of pressure for the fins by using this thick equation. No worries, you should have all these variables already if you've measured your dimensions properly, and each one can be found in this handy diagram. If you're like us and used elliptical fins, then your diagram will look like this, and triangular fins like this. The only variable not shown is n because that's just your number of fins. For these equations to work, n can only be equal to 3, 4, or 6. Otherwise, well, the equations won't work. Once again, we have a one and done equation whose value I'll again set aside. Next, we need the interference factor of the fins, or a value saying how much the fins slice through the air. For 3 or 4 fins, you can use this equation, and for 6 fins, use this one. Again, you have all your variables, with r being your body's radius, and we can now find the center of pressure for the body and fins, which is just the center of pressure of the fins times the interference factor. So now, the centers of pressure are married and absolutely inseparable except with a divorce paper called a division sign, but we won't be doing that. We aren't done yet though. We still need the distance from the reference line to this center of pressure, called x bar f, which stands for fins. That can be found with this, which is the distance from the reference line to the top of the fins, plus a whole bunch of other garbage that I didn't bother figuring out what it meant. Finally, we only have one thing left to find. Just take your centers of pressure and add them together for a total. Now we can plug all of our variables into this big equation and get our result, which is a distance from the reference line. This is your center of pressure. Ladies and gentlemen, we got them. Oh, you thought I was going to let that NASA site slide under me? Here you go, big ol' equation. This is the other method, and this one can use any amount of fins. It doesn't discriminate at all. This defines the reference line at the bottom, though, so be mindful of that. Anyways, this is easier than the last one, as it's literally geometry. It's also another, wait for it, weighted average. Projected areas times their respective distances from the reference line all over total area. But what is projected area? Let's take a look at a projection right now. If I take a flashlight and shine it on a cube, its shadow is a square. That's a projection. So you can see a projection is just a two-dimensional figure over a three-dimensional object. You can also have 3D projections, like how a cube is the projection of a tesseract, but that's the wrong science again. Anyways, the area formulas now become insanely simple. Mostly. Depending on your shape, you might need some basic geometry to get things done, like we had to split our fins into a rectangle and half ellipse, but you get the point. The hard part is the nose cone. You could be lazy and approximate it to be a triangle, and on a model scale that doesn't change much in the equation itself, but we didn't do that. Instead, we found an integral that matches pretty close to our nose cone's shape, because remember, an integral is area under a graph. So we took our basic radical x curve and used guess and check until the y value at our nose height, which was our x-axis, was equal to our radius. That came out to be this formula. With that, we can use our cone's height as x, multiply it by 2, and we're done. We now have the area of the nose cone. Now we just measure the distance from the reference line to the center of each component. Once we've done that, we can finish off that right side of the equation. Remember how I said you can use any number of fins? As long as they're equidistant and identical in shape, just multiply the area of one fin by your number of fins and boom! you've got the area of all the fins. Now you can take the big old number you got on the right side and divide by the total area, again making sure you multiply by number of fins, and you have the distance from the reference line of your center of pressure.